While we're working on Season 2 of Where What If Becomes What's Next, we'd like to introduce you to a new Carnegie Mellon University podcast, Does Compute, from our School of Computer Science, where CMU experts, alumni, and students, along with host Stephanie Stricklen, will explore what's next in computer science, robotics, and artificial intelligence. In this sample episode from Does Compute, the first of a two-part episode on robots in space, CMU Assistant Professor Zach Manchester discusses nano and swarming satellites, what they're doing now, and the role they're going to play in the future of space exploration. You can view additional Does Compute episodes online at cmu.edu/news/podcasts or subscribe to Does Compute on your favorite podcast portal.
We are here to talk about robots in space. And joining me right now is Zach Manchester. He is with the Robotics Institute at Carnegie Mellon University School of Computer Science. Hi, Zach.
Hi.
Thanks for making the time to be here with us today. Can you start by telling me about your journey, how you ended up in the field that you're in now?
Yeah, I think it's like a kind of stereotypical story. I was the classic space nerd, airplane nerd as a kid. I was obsessed with rockets and airplanes growing up, the usual. So it was almost there was almost no other path I was going to end up. I was going to be an engineer or a pilot or something, from earliest childhood. Yeah, so I had that growing up, and then went to school I actually did my undergrad in applied physics at Cornell. And then sort of minored in aero, and then ended up doing a master's in aerospace, PhD in aerospace, worked on all kinds of little satellite things in grad school, spent some time at NASA. And, I don't know, I think the path was always from as early as I could talk, or any of that stuff. As soon as I was a sentient being, I was obsessed with airplanes and spaceships and stuff.
I love that because you've accomplished really both of your childhood goals, right? You got your private pilot's license and now you're working in this incredibly dynamic field. I want to talk to you a little bit about what you are working on right now. What was your aha moment that made you think to yourself, what I think we should work on is autonomous swarming satellites?
Going back to my grad school work, which was in really, really tiny satellites. So I've got a couple of these here poking around. So I did this as a PhD student. We call these chipsats. They're little 3 by 3 centimeter, 4 gram printed circuit board satellites. So I did this. We had a whole thing. I Kickstarter funded these things in grad school, and we launched a little over 100 of them in low Earth orbit and kind of flung them out. And kind of really early on in that project, the idea of having a whole bunch of these really cheap, tiny satellites where you could have hundreds, thousands, maybe, tens, hundreds of thousands of these things because they cost a few dollars each. It gets you to this perspective of, well, if I've got a whole bunch of these things, the obvious thing to do with them is to kind of network them and see what can you do collectively with these things that you could never do with one alone. So it's kind of this strength in numbers angle. And so, yeah, it goes way back to that kind of early work that I did as a PhD student. And more broadly, there's been a, say, 20-year-ish trend in the aerospace field of satellites going smaller and smaller. It's kind of started in the early 2000s with the CubeSats, if you've heard of these. Most people have heard of these at this point. So this was a standard for kind of 1 kilogram little 10 by 10 by 10 centimeter satellites that originally came out of Stanford and Cal Poly as a way to get students to be able to build satellites and actually see them fly before they graduated, a thing that could get from start to launch in a couple of years. But that kind of really exploded and in many ways changed the whole industry. And brought costs down, brought sort of life cycles of missions down to a year or two. And there's a thriving startup ecosystem around this, and it led to smaller launch vehicles and the whole other thing. But really that whole trend of, smaller, cheaper, faster missions, I think has opened people's eyes to this possibility of, well, if we've got smaller, cheaper satellites now and launch costs have gone down, we can really realistically think about deploying large numbers of these things. And so that's all kind of, I think the industry broadly has been thinking a lot about this in the last 20 years as a sort of byproduct of this going smaller, going cheaper. It's only been possible to have, tens or hundreds of satellites, thousands now with, SpaceX doing Starlink coordinating in some way.
How do you deconflict these in space?
Yeah, so this is a hot topic right now. So the short version of it, for these little tiny things that we're doing, they have no propulsion. They can't do anything. So the short version is there we don't, because we can't. And there's a whole conversation to have around space debris and how we kind of are trying to be responsible with that stuff. In our case, we're flying these really tiny things. We actually are deploying them at very low altitudes where they re-enter relatively quickly within weeks or months. So they're kind of like self-cleaning. But more broadly, a huge issue with scaling these mega constellations that are kind of happening now with, if you're familiar with Starlink from SpaceX, they're trying to fly tens of thousands of spacecraft in low Earth orbit to sort of blanket the Earth with satellite communications coverage. And there's obvious and really challenging issues there with what people are calling space traffic management. This idea that collisions are going to become more and more probable as you throw more of this stuff up there. And what do you do about it? So right now, there's a few things people do about it. Historically, there's a group sort of part of the federal government. It used to be called JSPOC. They run tracking radars that try to track everything in low Earth orbit that you can see with these radars, which ends up being anything that's bigger than 5 or 10 centimeters. It's kind of the small size scale they can see. So they track everything. And they do what they call conjunction analysis. So they have this massive catalog of all the stuff in low Earth orbit. They predict ahead by a week or two at a time. So, come in on Monday, run the simulations, predict the whole catalog out 2 weeks, and look for things that go within a certain, minimum threshold distance of each other. It's called a conjunction. They look for all these conjunctions on this kind of week or two time horizon. And then if it looks like anything that's an operational satellite, they'll go warn the satellite operator and say, hey, you might want to think about maneuvering your satellite to avoid this conjunction. So that's what people do now. There's increasing efforts to automate that process because as more stuff's up there, these are becoming more and more frequent, and it's going to get harder and harder for these things to be so manual and so tied in with the operators having to plan at a human timescale to do it. So there's been a lot of work in autonomous collision avoidance for these mega constellations like Starlink, where the satellites can kind of try to figure out how to maneuver on their own to stay out of each other's way. So that's kind of pretty nascent frontier stuff that people are working on.
You can certainly see the relevant applications for AI in a situation like that to provide support where humans, at some point with the volume that will be up there, will require a pretty robust system to stay ahead of it.
There's a huge scaling issue, right? One way to think about this, if you think about collisions, if you have two objects, there's sort of two things can hit each other, but it sort of scales like quadratic. Like if I have 10 things, the number of possible things that can hit each other there is like 10 squared. So it scales in a nasty way where you have to check pairwise all these possible collisions. And if you scale up, if you're talking about putting tens of thousands, hundreds of thousands of these satellites in low Earth orbit, it's going to get really crowded. And the raw sort of computational problem there of checking all this stuff over a reasonable time horizon, it gets really hard.
I'm glad I asked. Now back to the fun stuff. Why swarming satellites of this size?
Yeah, of any size, really. And I think there's a few key things there. One is there's phenomena that you might want to sense. And there's a bunch of examples we could talk about where you fundamentally need multi-point measurements. So examples of this would be, so if you only have a single satellite, let's say you're trying to measure something in the atmosphere where it's varying spatially, right, over the Earth. And it's also varying temporally, like it's changing in time. If you only have a single satellite, you're getting a data point as the satellite moves. And you can't tease those things apart, right? Because of the motion of the satellite, if I measure something now and 10 seconds from now, I can't tell if that's temporal variation where the underlying thing's changing in time, or if it's spatial variation and I'm moving and I'm seeing a difference from point A to point B, right? So if you want to tease these things out, if you have things that are both spatially and temporally varying, you kind of need multiple instantaneous measurements. You need like an instant snapshot to kind of tease this stuff out. So there's lots of good examples of this kind of weather, climate, atmospheric stuff comes up. There's similar things that go on with space weather, heliophysics. People talk about like trying to study the solar wind and interactions with the Earth's magnetosphere. All kinds of things you could imagine where just trying to get this kind of instantaneous multi-point snapshot of something that's happening is important.
Tell me about your work specifically then. Am I pronouncing it right? Is it Pi 4?
Okay, yeah, Pi 4 is a mission that's on orbit right now that was built mostly by one of my now former PhD students, Max Holliday. It started out when he was a PhD student with me at Stanford, And then he graduated a year and change ago and then went to work full time at NASA to kind of finish this off. So this is a 4-satellite mission. It's 4 of these CubeSats that are about 1 kilogram and change. So they weigh, I don't know, like 3 pounds or so, and they're about this big. So think like, I don't know, the size of like a loaf of bread or something like that. And these things have a bunch of cool things happening. So there's 4 of them that get deployed together. They have cross-link communication, so they have the ability to talk to each other in space. And on top of that, we can measure the time of flight of the radio signals sort of traveling from one satellite to the next. And by taking that time measurement, we can basically multiply that by the speed of light, which is how fast the signals propagate, and get a distance. So we can measure how far apart the satellites are and get these range measurements. And with that, and doing a bunch of fancy math and taking into account like the orbit dynamics and things like this, we can back out their positions relative to each other. So we can kind of triangulate their relative positions using these range measurements. So this is kind of the first step towards doing any sort of coordination between these things, right? Just knowing where they are in relation to each other. If you want to coordinate their measurements, and understand where they're taking measurements. If you want to start doing things like formation flying, this is a really basic thing you need to be able to know, right? So we're doing that, sort of using this range data and then processing it in fun ways to figure out where they are. We're also doing a whole bunch of things related to, going back to like I have this long kind of history of trying to make these things smaller and cheaper. We're doing some fun things with actuation on these guys, kind of in 2 different ways. So classically, if you wanted to formation fly a bunch of satellites like this, you would need a propulsion system. And when we get down to these really tiny packages, these little tiny CubeSats, that gets really, really hard to do for a bunch of reasons. One, it's just hard to fit all that stuff in there. As soon as you talk prop, you're talking, generally speaking, chemicals and valving and all kinds of plumbing, right? And it gets really complicated. It gets heavy, it gets expensive. And kind of automatically, you're kind of leveling yourself up out of this CubeSat form factor into something a lot bigger, heavier, and ultimately way more expensive. So we're trying to get rid of all that cost and complexity and avoid a prop system. So what we're trying to do on Pi 4 is formation fly these satellites without a propulsion system, which sounds kind of nuts. Like, how do you even do that? So the answer is we're playing games with atmospheric drag. And so the analogy here would be something like a sailboat. So we're in low Earth orbit. There's still really thin air. There's not a lot of air, but there's still thin air. So you get little tiny forces. And these Pi 4 satellites have deployable solar panels. So they think about them like wings, right? So they're all tucked away when we deploy them. And then when they get out in space off the rocket, these kind of solar panel arms unfold. And so you can think about them like they've got a good amount of surface area. Think about it like a sail or a wing. And we can basically fly the spacecraft kind of edge on to the wind or face on to the wind. You could think about this like, putting the brakes on. If I sort of angle it such that the fat solar panels are facing the velocity direction, I'm going to get a lot more drag. So people have done stuff like this before, manipulating drag to change orbits. And in particular, there's a startup called Planet that's been doing this for a few years. They have a big constellation of a couple of hundred CubeSats that are doing Earth imaging. The way they do this, they deploy, say, 20, 30, 40 of these things at a time in a big clump. And then they do clever things to manipulate the drag so they can string them along in a sort of line or ring. String of pearls formation is what this is typically called. So that lets you spread these guys on a line. It's kind of obvious you could do that, right? Basically, you have brakes. You can hit the brakes. Unfortunately, that string of pearls formation doesn't let you do certain kind of sensing things. In particular, one of the things we're really interested in is navigation, positioning, this kind of stuff, where you want to take these kind of range or time of flight measurements and turn those into positions. It turns out if everyone is in a line, you can't get a 3D position fix. You need cross-track separation. You need basically separation in multiple directions to do triangulation. So we want to be able to formation fly these guys, not just in a line, but also in maybe, say, a box formation or something like that, which naively, if you've only got brakes with this drag stuff, you can't do. So we've basically figured out a way to do this. The rough analogy, I would say, it's a very rough analogy, would be like tacking and sailing. So you want to kind of fly, somehow you want to get forces in the direction perpendicular to the wind. You want to fly sideways with respect to, which is how a sailboat tacks, right? We don't exactly have this kind of thing going on. What's going on instead is some kind of complicated interactions with the Earth's gravity field, which if you're up for a nerd out on this, we can do it. So
very much so.
The Earth is not a perfect sphere. It's almost a sphere. And so but mostly to like the next term in the expansion, if you like, and the gravity field is this thing called the J2 effect. And roughly what this is the Earth's spinning. And because of the spin, it kind of gets a little bit squished. So it's a little bit fat around the equator. And there's like an extra bunch of mass around the equator. Actually, if you measure the radius of the Earth from pole to pole is, I want to say maybe 20 kilometers shorter than from equator around the equator because of this kind of squashing effect. So there's this extra fat around the equator. And what that does to orbits, if you think about an orbit kind of going around the Earth, like maybe, near equatorial, like, or near polar, kind of around like this. If you think about it when it's up, like sort of in the northern hemisphere, this extra fat around the equator is pulling down on it more. When it comes around the other side and it's, say, down over the South Pole, it's getting pulled up towards the equator, right? So that's actually generating about like a torque on the orbit. It's doing this. And this causes this thing called nodal precession. Basically, it causes the orbit to spin around. So this is a known thing. What ends up helping us here is that effect is altitude dependent. So the lower you go, the stronger the effect is because you're closer, which kind of makes sense. So what we do is we take these satellites using drag. We can kind of hit the brakes. We can lower the orbit using drag. So if you have two satellites, we can kind of hit the brakes on one and drop its orbit down slowly. As it goes lower, that precession effect speeds up. So it starts to kind of clock the orbit around. We wait for that to get where we want it, and then we drop the first satellite back down to match it again. So this way we get cross-track separation, and we can make kind of arbitrary, say, 2D formations. We kind of line them up this way and in the cross-track direction as well. So we're trying to do stuff like this on Pi 4. We're trying to do sort of ultra low cost, be really clever with actuation and avoid expensive things like prop systems.
I am so beyond impressed and thrilled at human ingenuity at any given time, and especially with this project. The way you describe it is very approachable. So I feel like I understand something that is actually insanely complicated. So thank you for making that something I can follow along with. What do you see? So right now you're working through the mechanics of these particular cube satellites, making them work, swarm, communicate, adjust their speed and location. What is the ultimate value for humanity? What problems are you trying to solve?
So one of the big motivators for Pi 4, there's a reason there's 4 of them, and there's kind of a reason we're working on this box formation problem. Again, going back to like navigation and positioning stuff. So everybody uses GPS. People know about GPS. The way you get positions out of GPS is you do this triangulation thing. You measure time of flight of radio signals. It turns out you need at least 4 satellites to get a position fix, and you need them to be spaced out in a certain way. So the reason for this, you might think, basically you're trying to get an XYZ position. There's 3 numbers you need there. So you need at least 3. It turns out you're measuring time of flight, and it turns out there's an extra time variable you have to estimate out as well, which is basically a clock offset. So if you had a perfectly synced clock, like if everyone had atomic clocks, in their phones, you wouldn't have to estimate that out as well. But because of the timing precision you need and the fact that you don't have an atomic clock, you basically have to back out this clock correction term as well. So there's 4 numbers. You need X, Y, Z, and time to get a position out of GPS. So that means you need 4 numbers. You need 4 satellites. You need 4 of these range measurements. And because of geometry, they can't be in a line. They have to be kind of spaced out enough. In GPS speak, this is called dilution of precision. Basically, as those satellites start to kind of get too close together overhead, you lose accuracy in your position. And if they kind of are lined up, you can't get a position anymore. Okay, so that's kind of the formation flying angle, the position angle. That's where 4 comes from. What we're trying to do with Pi 4 is actually get towards a system that can do this kind of triangulation stuff, sort of like GPS, but backwards. So GPS transmits from the satellites, and then the receiver on the ground listens and figures out where it is. So this is great if you're in a car or in an airplane and you need to know where you are. But if you flip this around and you look at applications like wildlife tracking, which is an area we've been heavily involved in for the last couple of years, if you want to track birds or whales, which is super important for climate change and things like that, the whale doesn't need to know where it is. The researcher sitting at some university or government lab needs to know where the whale is. So having a GPS receiver on a whale does you no good. Basically, this thing's sitting there in the ocean, listening to the GPS satellites, and it has to have not only a radio receiver to listen to the satellites, it then has to have all the smarts to take those signals, do a whole bunch of signal processing and math and compute this navigation solution where it is. And then the whale knows where it is, or the tag knows where it is out in the middle of the ocean. It doesn't help us. So then you need another radio maybe to ping some other satellite to bounce the signal back to the researcher who ultimately cares about it. So this is how it's currently done. And it means that these tracking devices are way bigger, way heavier, way more power hungry, and way more expensive than they need to be. In fact, like if you go out and commercially try to buy these things, they look like a little brick. They're like, waterproof and all this stuff. They cost about $5,000. And there's a bunch of other issues, but just that, right, really limits what you can do. And so if you kind of flip this around and instead have the tags on the whale, for instance, transmit instead of listen, now it can be a super dumb little beeper. It doesn't have to think about anything. It doesn't have to know anything. All it's doing is, collecting energy from a solar cell or whatever. And as soon as it has enough power, it just pings little radio, beep. And then the satellites overhead listen. And now all the smarts are on the satellites or on the ground ultimately. And the satellites just kind of, when they go over the ground station next, send this and the researcher gets what they want. So that's one of the big applications we've been pushing for. And that's why 4 satellites, that's why they have to formation fly in a certain way. So one of the big applications we've looked at is building a global wildlife tracking system that can track things like, birds that are there's all kinds of examples of these species. They're crossing international borders. They're crossing oceans. They're going halfway around the world twice a year. You just can't track these things with ground-based infrastructure. It has to be from space looking down, right? These, like the classic example of this I love to pull out is the Arctic tern. These birds go from the North Pole to the South Pole and back every year. And they're going over open ocean and everything. You just have no idea where they are, right? And there's tons of examples like this. So to really get the picture you want, this kind of global picture, you need to look down from space. So that's one of the drivers. And I think more broadly, there's a ton of areas where you want this kind of tracking ability, positioning ability, and there's reasons why GPS isn't ideally suited to it. And you want to kind of flip the story around.
How collaborative is an effort like this ultimately? You mentioned crossing, we're in talking about the Arctic tern and other animals moving across borders and with those limitations. How important is interdisciplinary and collaborative efforts to the ultimate success of this project?
Yeah, I mean, it's huge, as you can imagine. Right? So we've worked there. We work with, obviously, we've collaborated with NASA for years on this stuff. We've also collaborated closely with people at the Bureau of Ocean Energy Management, which is a government agency that is basically in charge of everything on the continental shelf. So everything like at a certain distance of shore, and they track turtles and whales and birds. We've collaborated with other folks who are ornithologists who are interested in bird tracking. So yeah, tons of different folks. And ultimately what we bring to the table, in our group, we're good at, kind of these navigation things, control things. We're good at the math. We do some of the hardware. We do, satellite hardware stuff to some degree too. But, the applications are all coming from other people, right? Like I don't know anything about, how to tag a bird or a whale or whatever. So we've collaborated with folks who actually go out on buoys, or like harpoon these guys out on like little boats and stuff and ask them, well, part of the story here, if you're trying to design a system like this is, well, how long do whales spend on the surface? How long are they underwater for? Like, I don't know any of this stuff. So there's a ton of stuff that, ultimately to do anything like that takes a huge range of expertise that nobody's got on their own.
How is AI/ML helping you get ahead of the vast amounts of data that this project will be able to collect?
I mean, honestly, we're not on that side of it, but that's totally right. If you were to build this system and be able to track these kind of species globally at scale, the way that's the dream, right? We want to get these tags down to sub $10 price points where you can deploy them by the millions and tag everything, right? And understand where these things going, where's the food, where is there illegal poaching going on? That's another huge issue. Right now, there's like almost no way of enforcing like illegal fishing in international water, stuff like this. Like these guys in these boats turn off their transponder, they're invisible, right? So if you want to do enforcement efforts, like it's a huge thing. So yeah, and getting at that data, once we have the data, you're going to need to be able to use sophisticated data analytics techniques and kind of these ML techniques to understand it, right? Make sense of it. I'll say like we're very much not on that side of this problem space, but we do work with folks we have who are. So there are people out there who actually in the ecology conservation space who spend their careers doing like AI ML for these kind of applications, mining satellite data and stuff like this. We worked closely for a few years with a woman named Arlie Shapiro, who was at the time at the World Wildlife Foundation, whose whole thing was basically guilting satellite imagery companies into giving her free image data from these satellites and then using it to try to figure out, well, where is there illegal logging going on? These kind of questions, right? And it was kind of taking the data, this huge amounts of image data that get collected every day, and then figuring out, like, if you have a question like this, you're not going to sit there. One person can't sit there and sift through a week's worth of satellite imagery. You have to figure out how to take your question and leverage these kind of tools to understand what's going on in these large, data sets.
Another interesting example of the collaborative nature of it, right? It's not only just from a policy and boots on the ground deployment standpoint, but also the back end of it when you do collect the data. You mentioned earlier, this is only one of a number of projects that your lab is working on. Can you tell me about some of the other things that just get you really fired up in the space?
Yeah. So one of the other big kind of themes, going back to the AI ML thing that we've been working on lately, also related to navigation, which we, I guess, have a thing for on the space side of things. We're getting into vision-based navigation for satellites in the last year or two. And so the idea there is, there's reasons to care about this around Earth, but if you're going beyond Earth, if you're going to the moon, if you're going to Mars, you don't have GPS anymore. And how do you figure out where you are? So the way this happens now, for the most part, is with something called the Deep Space Network. This is a bunch of dishes that NASA operates around the Earth, big dishes that talk to all of the deep space spacecraft that NASA and ESA has their own stuff too, and they work together. Basically, these dishes talk to all the satellites that are, out in deep space. And the way you get position from these things is basically by measuring things like time of flight of those radio signals. So you can measure range with time of flight, and you can measure range rate, basically the velocity along that radial direction with radio signals. That does not give you a full position, right? That kind of tells you, oh, I'm this far away in this, maybe vaguely this direction. So to get a full position out of that is really hard. It takes a lot. What you're basically doing is taking lots of those measurements over time as the spacecraft moves around, and you combine that with knowledge of, the Earth, the gravity fields and, the dynamics, how these things move. And you take a whole bunch of that data and do a bunch of fancy math and ultimately can get a position estimate. But those estimates are not great. So for context, typical errors of, like when we go to Mars and we try to land on Mars, when one of those spacecraft hits the Martian atmosphere, its position uncertainty is maybe around 1 kilometer. So it's way worse than GPS, right? And it takes a lot of effort to get that to happen. So if we want to do, for instance, we had a project for a while on precision landing for Mars entry descent landing. Like, NASA wants to put crewed spacecraft on Mars when they eventually send people there to within 50 meters. That's the stated goal, which if you have GPS is easy, right? SpaceX lands rockets on a barge within 10 meters. But if you're at Mars with no GPS, how do you get to 50 meters? It's a huge challenge. So one of the ways people are looking at doing this, and we're looking at doing this, is by using imagery, using cameras, and then using map data, existing imagery, to identify landmarks in what you're seeing with your cameras and correlate those with known, like you take what you see in the camera and try to correlate that with known landmarks, their location on a map. From that, you can get some bearings. And, if you have enough of that stuff, enough of those landmarks that you can see, you can figure out where you are. So we've been working on this for a while. We've got an Earth version of this working right now. And it turns out Earth is the hardest case, which is kind of why we started with Earth, because of clouds and weather and seasons. So at any given time, about 50% of the Earth is covered with clouds. And that's all time varying and messy. And then also seasonally from, June to January, the same spot might look green, brown, or white, and depending on, what's going on with rain and snow. So that makes it really hard to do at Earth. If you go to the moon or Mars, no clouds, no weather. It looks the same all the time. So it's actually a way easier problem. So we've got the kind of an Earth version of this worked out, which we're actually hoping to test in the next year or so, follow-on satellite that we're building now. Here at CMU with a collaborator in ECE, Brandon Lucia, we've been doing this. We actually ran this as a class this past year and had a bunch of students working on this, like designing the satellite and building a bunch of stuff. So it's going to be another little CubeSat with 6 cameras on it. It's got a camera out each face. So it kind of gets a full 360 view of everything. And then, looking down at the Earth and looking out at the stars and taking information, like identifying unique landmarks, unique stars, taking all that and then ultimately backing out both its orientation and its position with no GPS.
This is an aside, but I'm in a rabbit hole and I'll get right back out of it. And I probably have this wrong, but in my head, when you're discussing this, I'm thinking about deploying something to Mars. Mars has its own set of gravity and it does have its own set of weather, even if it doesn't have an atmosphere. But these CubeSats don't have propellant. Would there be a way to launch them in Mars and do the exact sort of low orbit mapping that you are doing with P4, even though maybe the drag variables and the ways that you're navigating now don't exist?
So there is some atmosphere on Mars. It's way thinner than on Earth. I haven't looked at the drag stuff and whether that kind of drag-based formation flying stuff is viable around Mars. So I can't give you a good answer there. It might be, might not be. It might be super impractical. There's other ways to get at it, though. So, I mean, you can obviously just build a bigger satellite with a prop system. And, maybe that's what you end up doing in that context. Another thing we're looking at, though, that I'm pretty excited about, which seems like it may work out in the moon context. But again, back to like, how do we make these things smaller, cheaper, et cetera, is actually solar sailing to do this instead of drag, right? So you're probably familiar with this, but like people have flown solar sails. You big shiny mirror thing, and you kind of get momentum from photons from the sun, right? And the analogy there to sailing is really good, actually. It's pretty much sailing. It turns out like what people have looked at for years, though, is trying to actually do, large maneuvers with solar sails, like go from Earth orbit to the moon with a solar sail, which is a huge amount of delta V. You need a huge amount. So if you try to do something like that, you need a gigantic sail, and it becomes pretty impractical to build a sail that big. But if you're talking about the sort of thing we're doing with drag, with Pi 4, we're talking about really tiny forces. And really what matters there is the difference in forces between pairs of satellites, right? So we're not trying to massively change the orbit. We're trying to tweak it just a tiny amount between these two satellites to move them relative to each other. It turns out if that's the sort of thing you're trying to do, you don't need a lot of sail. Actually, you can get away with maybe even just a few square meters, which now looks super doable in a CubeSat package. So that's a way you could get at this, for sure at the moon, which is something we've been looking at recently. And then maybe, that sort of thing can work at Mars too, for this kind of formation keeping control stuff where you maybe don't have atmosphere.
Zach, my last question to you is, what do you love the most about your job?
I just like playing with my toys. That's why we do it. I mean, like that solar sail stuff, we're actually doing that right now in collaboration with JPL. I have a student that's there for the summer who's been working on this for a bit. And we're trying to do that stuff. We're basically developing the algorithms so that one of these little satellites can do this autonomously, like can do all the calculations to do it on board without having to phone home to Earth. So it's all, I think that everything we're doing is kind of geared towards, onboard autonomy. Like how do we make these things smarter so that they don't need to phone home all the time and have a human in the loop? And then how do we make them smaller, cheaper, all this kind of stuff, more capable, all of which is geared towards how do we scale these things, right? If I want to have 10,000 of these things floating around the moon, all 10,000 of them can't be phoning home to Earth all the time to ask where they are, to ask a human to like avoid collisions, to ask, all of that stuff, right? So it's all tied together. Like they need to be more autonomous so that they're not reliant on comms back to Earth and humans. They need to figure out where they are without phoning home. And we need to make them smaller and cheaper so we can get to those kind of scales. So I think the biggest thing for me, like why I do this and why I'm not at NASA or at a company or whatever, is that I get to like this conversation sort of really kind of is kind of testament to that, I guess. I like having like my hands in 10 different things at the same time all the time. And I think, in any other context, it would be maybe one or two things. And this, in this job, I get to kind of like have an army of students and like, everybody's kind of working on a different thing. And it lets me dabble in, 10 different things all the time, all at once, which is, for me, I have like, I get distracted easily by shiny new things and like, bite off lots of, fun problems. And that to me is kind of the reason I would do this over a lot of other things.
Zach Manchester, thank you so much for your time and perspective.
All right. Thanks.
You've been listening to Does Compute, the podcast that examines how computer science is building useful stuff that works. Thanks so much for joining us. I'm Steph Stricklen.